Welcome to Colaberry AI Podcast, brought to you by Colaberry AI. Despite massive investments in machine learning across the industry, most enterprise AI initiatives stall at the pilot phase. There is a persistent delta between the theoretical capability of these models, often demonstrated by high benchmark scores, and their actual automation output in a live corporate environment. The root cause of this failure rate is technical framing. Organizations treat AI as an isolated technology problem rather than a structural architectural challenge. This diagram shows the exact point of failure. By injecting a probabilistic feature, like a standalone large language model, which generates outputs based on statistical likelihood rather than strict rules, into a deterministic, rule-based enterprise workflow, the system immediately generates cascading red error states. A single node cannot manage the branching logic to execute complete business processes. To achieve functional automation, we must examine systems operating at scale. We are tracking an architecture of 88 autonomous agents, processing enterprise data in real time. This 3D network graph maps the required topological shift. True automation abandons the single node and divides the architecture into 3 strict horizontal strata: workflow execution at the bottom, intelligence in the middle, and platform system at the top. Achieving autonomous workflow execution requires abandoning feature-level integration entirely for this strict multi-layered system design. Focusing on this bottom stratum, we isolate the execution layer. This network of interconnected nodes is strictly responsible for end-to-end workflow processing. Consider a standard university admissions department. Assigning an entire lead generation workflow to a single chatbot node guarantees a bottleneck, as one agent attempts to handle context, user intent, scheduling, and compliance simultaneously. Instead, this execution layer distributes that operational burden across a coordinated system of 27 precise microagents. These agents operate via sequential routing. They pass state logic forward as a data packet moves step by step through the system. When a new lead arrives, the visitor activity agent detects initial behavior, handing data to the intent detection agent to score immediate interest. The packet then routes directly into the conversation memory agent, ensuring total historical context is preserved. With context established, the conversation planning agent takes the packet to determine the precise next action. Finally, the sequence cascades through the proactive outreach agent to execute the follow-up, callback agent to secure a meeting time, and compliance agent to verify quality. In a properly architected execution layer, no single agent holds the operational burden. The system itself is the solution. Execution cannot function autonomously without a dedicated layer for decision logic. As this middle intelligence layer illuminates, dense streams of data telemetry flow upward from the execution nodes into the analytical stratum. This layer operates at significant scale, utilizing 37 specific agents dedicated solely to abstraction and analysis. The core mechanisms operating here are continuous pattern detection and predictive forecasting. For example, intent scoring mechanisms actively identify high-value data nodes in the stream and route them for immediate priority. Simultaneously, opportunity scoring governs queue prioritization, dictating exactly which tasks the execution layer below it must handle next. To prevent logic breakdowns, campaign health agents continuously monitor the streams to perform real-time anomaly detection. Above that, forecast engines run probabilistic outcome models, adjusting system behavior and resource allocation before failure thresholds are ever reached. Without a dedicated intelligence layer, companies force AI models to act without building the cognitive system required to decide how they should act. Scaling multi-agent systems introduces a hidden technical debt, inevitable state decay, and runtime errors as complex data packets collide. This top stratum illustrates the platform and system layer, tasked entirely with infrastructure maintenance. Here, descending feedback loops actively replace failing red nodes with healthy green ones. Resources are strictly allocated for this task. 24 agents operate in this tier with a singular directive: to maintain platform stability. Active auto repair protocols handle logic breaks seamlessly. The platform fix agent isolates and resolves corrupted decision pathways instantly. Uptime and overarching system health are continuously managed by the system resilience agent to prevent cascading failures. This autonomous, self-healing topology replaces the legacy approach of humans manually managing performance dashboards. A system cannot scale to enterprise production levels if relying on human intervention for error recovery. It must be architected to govern its own state. This split screen shows the complete 88-agent network operating in simultaneous harmony on the left, paired with a human mapping a decision tree on the right. There is a misconception that building a network of this scale requires mastery of discrete programming languages or prompt engineering. The true requirement is an intimate, rigorous understanding of human business logic and the exact locations of workflow inefficiencies. The design process involves translating human decision nodes, process drop-offs, and required outcomes into a cohesive digital structure. Executing this translation demands a specific emerging enterprise role, the AI systems architect. The AI systems architect serves as the critical integration point between raw enterprise data, operational decision automation, and multi-agent system design. The ultimate bottleneck to enterprise AI is no longer technological capability. It is the severe scarcity of systems-level architectural thinking inside organizations. AI underperformance in the enterprise directly correlates to isolated, feature-level integration, rather than fundamentally redesigning how work actually happens. As this diagram illustrates the network collapsing into a central core, we see that true operational optimization requires mapping exact workflows into coordinated, multi-layered agentic topologies. To succeed in production, these systems must be explicitly designed to autonomously govern, predict, and repair themselves. Technical managers must stop buying isolated AI features and start architecting unified AI systems. Thank you for listening. Subscribe and follow Colaberry on social media. And check out our website at www.colaberry.ai/podcast for more insights like this.